A system can be described in two broad ways, in logical terms and in physical terms. A logical description, historically we've often called that a functional description, articulates what the system will do, how well it will do it, how it will be tested, under what conditions it will perform, and what other systems will be involved with its operation. A physical description relates to the system elements themselves. It explains what those elements are, how they look, how they'll be manufactured, how they'll be integrated, and how they'll be tested. So a logical description is about what, and a physical description is about how. But both those descriptions, of course, are very important, and they both exist together. And both of them require what we call later a series of statements called requirements. Now, the two descriptions are valid, independent descriptions of the system, and it's very important that the system is described both logically and physically. But of course, we must focus first on the logical description. Now, in one sense, it's axiomatic that we develop that logical description first in order to determine whether any particular physical system is appropriate, that is, how we're going to do it is useful to us. We must first understand, of course, what it is we want to do. What purpose do we want the system to serve? We therefore need to focus on the logical description, the what, before we examine a series of candidate physical descriptions, the hows, of how we might develop the system. One of which, of course, is going to be chosen as our preferred physical solution. The second reason is we must also not allow the way in which we currently implement current systems to colour unnecessarily the way in which we describe future systems. If we focus on the logical description, we can then focus on perhaps novel solutions to new or even old problems. If we focus on the physical solution first, we would always end up solving new problems with the old physical building blocks. Third, if we're going to trade things off, if we're going to actually trade off value for money, for example, then we need to do that at a logical level before deciding on the physical implementation. If not, we may waste significant effort selecting physical solutions which either perform unnecessary functions or don't perform something which actually is critical. Next, a logical description is ideally suited to the interface between systems engineering and the business case. While it's often possible for the business case to be met directly by an obvious physical solution, it's probably better for business management to transition from their business case into a more detailed logical description before going on to deciding how to solve that problem in a physical sense. The definition of the logical description before the development of a physical system therefore moves from the business case to the final solution in a more controlled, more verifiable way. And the final reason is that the logical description changes much more slowly. The physical description changes very quickly, particularly these days with changes in technology. Arguably, for example, the need for and the upper level description of an internal combustion engine hasn't changed much over the last 2 centuries. Its purpose is to provide forward motion for the car. But the physical implementation for an engine has changed dramatically. That is, the purpose of the system as part of the car hasn't changed, but the way in which we do it has, as we avail ourselves of new technology. In the development of a system, therefore, there are the two architectural views, a system logical architecture and a system physical architecture. Now, of course, these two descriptions are of the same system, so they must be related. We'll see later how the logical architecture, as outlined in the requirements breakdown structure, is mapped onto the physical architecture as it's represented in what we call the work breakdown structure.